So we are going to cover some hard topics, and you're going to let me know what you don't understand, and then we can always cycle through them, right? They're the same topics that I have covered in previous videos, previous terms, slides, but these are all quick from a logic perspective. All right. So we're going to be talking, here's a bunch of topics, and if you go through our course, right, you can learn about Euclid and logic, you can learn about Hilbert and proof systems, you can learn about Gödel's incompleteness theorem, you can learn about Turing machines, you can learn about my father who talks about polytime and non-determinism, you can learn about Cook who does NP completeness, right? So we are going to do just a quick learning on those topics. So we classify computational problems based on how hard they are, right? So this is the class of all problems that can be done in polytime versus exponential time versus computable. And then we can talk about different types of uncomputable problems. And we can talk about problems that aren't in polytime, but NP problems and co-NP problems. So that's what we're going to talk about, define all of those. So let's talk about the idea of a witness. And a witness is something that if you want to prove that something exists, then the witness is the thing, you prove that something exists by giving you a witness and saying, look, here it is, right? Here it is, it exists. All right, so how did we do computation? Well, in the beginning, Euclid came up with the first algorithm. He came up with an algorithm for GCD, greatest common divisor, and they just felt, right, everything was possible. God could do anything, so it was just a matter of coming up with how to do it. And then Hilbert in 1920 said, hey, is every computational problem computable, or is there problems that are uncomputable? And then his graduate student, Turing, said he defined a computational problem to be something that could be done by a Turing machine or by a Java program, right? So if a Java, well, Turing, of course, didn't say Java because Java didn't come until 10 or 20 years ago. But the same idea. He says the problem is computable if there's a Java program. All right, so let's talk about a computable problem, all right? I'm going to give you a problem, a computational problem that's computable, right? So here's the problem. I give you, you're going to solve my computational problem for me, and I do a Java program, and I give you the code, and I give you an input, and I give you an amount of time, right? So those are the inputs to the problem. A Java program, an input, and time. And what I want to know is I want to know, what does the Java program, if you ran that Java program on that input for that length of time, what would the Java program do, right? Would it stop and output some great number? Would it run forever, right? That's the question. All right, so everybody think, is this I say it's a computable problem. Can you give me an algorithm for this problem? I don't have anybody's faces now, right? Think about, can you give me, give me an algorithm for the following problem. I give you code, I give you an input, I give you a length of time. I want to know what the program does in that length of time. What do you do?
A loop?
Just run the code?
You just run it. You just run it, right? So it's computable. Why is it computable? Because the algorithm is you just run it for t time steps, right? And you tell me what it does. Everybody follow that?
Yes.
All right. So I'm going to give you another problem, and this problem is uncomputable, right? That means there's no algorithm for it. Here we had an algorithm for that first problem. Here's a problem that there's no algorithm for. And Turing down here proves that there's no algorithm. What is it? It's, I no longer tell you the running time. right? I'm just asking, does there exist a running time such that after that amount of running time, it halts, right? So the input now is still a Java program and an input, but I just want to know, does it ever halt, right? So is there an algorithm for that? Well, what's the search space, right? You think, well, if I had a t, the algorithm is computable, right? For any given t, I can determine whether or not the algorithm Java halts in t time steps, right? So for every t, I can solve this problem, right? So I'm searching for a t that solves this problem, right? But how many t's are there? Well, there's an infinite number of t's, right? I could run it for 1 time step or 2 time steps, 3 time steps. There's an infinite number of t's. So it takes me an infinite amount of time to search all these t's. So that's why the problem's undecidable. Does everybody get that so far?
Yes.
All right. So now I'm going to give you another example. All right. This is what we're going to be doing here. We're going to talk about things that are computable and then search problems that are not computable. All right. So here's another problem. I give you some multivariate polynomial. What is that? Well, this is more of a circuit, but what do? You have input variables that are maybe real values. So x1, x2, x3, y, z are real values, variables. And then you have times and pluses. You have a polynomial that tells you times and pluses, right? So I give you one of these things. I also give you a setting of all the values, right? I tell you x is this, no, let's not have them be real values. Let's have them be integers, all right? Anyway, I give you particular values, right? Integer values. And what do I ask? I ask, well, if you plug in those integer values into the polynomial, does the polynomial evaluate to 0 or not, right? So that's a question. Is that a computable problem? Well, it says it's computable. So what's the algorithm? The algorithm is you follow the rules. Here, you just multiply, add, and here I have values up at the top, and you plug them in, bang, 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 you get an answer 20. It's not 0, so you say no, right? So is that a computable problem? Right? Well, now let's turn it into a search problem, right? Now I give you the polynomial, and I ask you, does there exist an I which sets integer values for all your variables such that the output is 0, right? For any given I can compute this quickly, but I'm asking, does there exist an I, right? Well, right, what we're asking is it satisfiable? Is there exist an assignment that satisfies it? Well, what's our search space? Again, the search space is infinite. So even if we're only searching over integers, right, then there are an infinite number of them, and the problem is uncomputable. Now, let me just tell you a little funny caveat. If we don't search over integers, and I did say integers. If we allowed them to be real numbers, then the problem is solvable. Why? Because then you can do calculus, right? There are algorithms for finding integers, real numbers. But integers are a lot harder because you can't say, well, there's a number somewhere between 5 and 6 that works, right? Well, because it either has to be 5 or 6. So anyway, this problem is also uncomputable, right? Is there an integer solution to a polynomial? All right. So let's look at our picture here. We have two problems which are computable, right? Where if we're given the Java program and the input and we're given the time, right? Does it halt in that much time? That's computable. If I give you the polynomial and I give you the setting of the integers of the variables, that's computable. But if you have to look for the time or you have to look for the integer solution, then there are an infinite number of them. So it's not computable. And there's a whole class of problems called acceptable, where here, the funny thing about this class, if the answer is yes, that there exists a t or there exists a setting of the variables, if you had a fairy godmother come down and give it to you, right? If they would tell you the time, if they would tell you the setting of the variables, then you could know quickly that the answer is yes, that there does exist things, right? If you were given a witness, then you can answer yes. But if you're not given it, then it takes you don't know how to search for it. Let's not get into it too much, but the flip side of exists is for alls. And so if you take the complement, the negation of exists, then you get for alls, and that's a class called coacceptable, right? All right, so what's true about the acceptable problems is, as I said, is about a witness, right? The I or the T is a witness, it's a proof, it's a solution to prove that P is satisfiable, right? I'm asking, hey, is P satisfiable? If you give me an instance, then that proves to me it's satisfiable.